We are already very comfortable with both probabilities of default and credit scores. But how do we decide who is granted a loan and who isn't? We will obviously take advantage of the estimated probabilities of default and scores we've already calculated. The cutoff rate is being used for taking a decision on whether to approve a loan application or not. If we set a given probability of default as a cutoff, all borrowers with a lower probability of default than the cutoff will be granted a loan. Analogically, all borrowers with a higher PD will be rejected. What is important to realize, though, is that a specific cutoff has two major implications. 1. Once a cutoff is chosen, it predetermines the total number of borrowers that will be approved and rejected. And 2. This cutoff impacts the quality of the loans the bank would grant. Naturally, there is a trade-off between the two. If we want to grant more loans, we will be inevitably accepting lower quality borrowers. The other side of the coin is that if we only approve the most credit-worthy borrowers, we will end up with very few loans. As you know, financial institutions that provide loans make money from lending loans and not from keeping their money safe. So the cutoff point is decided based on those two factors. How many borrowers would be accepted and rejected, and what would the creditworthiness of the accepted borrowers be? If a bank wants more business, it will set a lower cutoff in terms of creditworthiness or probability of non-default. And if the bank wants to lend to fewer borrowers with higher creditworthiness, it will set a higher cutoff point in terms of probability of non-default. All right. Now, apart from the probabilities of default, we also have false positives and false negatives. False negatives are borrowers that are predicted to default but don't. False positives, on the other hand, are borrowers that are predicted to pay their loan but actually default. In both cases, our model fails to predict that, which has a huge impact on the bank's profitability. Where do we get this information from, though? Well, remember the receiver operating characteristic, or ROC curve, we plotted when we were assessing the performance of our PD model? We used the ROC curve method with the actual good-bad variable from the test dataset and the probability of being good estimated by the PD model. The method returned three arrays: the false positive rates, the true positive rates, and the probability thresholds at which the respective false positive rate and the true positive rate was obtained. All of this data is useful for setting decision-making cutoffs. So, let's copy the code here and examine the ROC curve once again, this time in the light of choosing a cutoff. Let's create a new data frame where we'll store the data for selecting cutoffs. We'll start by storing the results of the ROC curve method in it. Notice how the data is arranged. The thresholds are in descending order, that is, starting from the largest to the smallest. Note that the ROC curve method sets the first threshold, where nothing is being predicted, to the maximum probability score from the supplied data plus 1. This row is not very instructive and won't be useful for setting cutoffs, so we can either drop it altogether or set the threshold to our probability, which is very close to 1. Let's do the latter, setting it to 1 minus 10 to the power 16. Okay. One common way to set cutoffs is based on the estimated probabilities to be good. Another one is through credit scores, as there is a one-to-one correspondence between the two. Since scores are much more interpretable, let's opt for them. We recently used a formula to calculate the probability to be good based on a score. Now we can reverse this expression to calculate a score from probability to be good. It goes as follows. The score equals the log of odds, that is, the log of the probability to be good divided by 1 minus the probability to be good minus the minimum sum of coefficients. This expression, in turn, is multiplied by the ratio of the difference of the maximum score and the minimum score, and the difference of the maximum sum of coefficients and the minimum sum of coefficients. Finally, the minimum score is added to the expression. Great! Of course, there is no probability as high as the probability we set the threshold on the first row to, so the score corresponding to it is very high and out of range. Therefore, we should place the maximum score on the first row. Okay, everything else seems about right. Now, let's see the approval and rejection rates for each possible cutoff. To calculate them, we have two options. The first one is to use the number of loan applications that would be approved. The second, to use the number of loan applications that would be rejected if a decision was made based on the respective cutoff. The second piece of information we need is the total number of applicants, of course. We treat the borrowers from the test dataset as new applicants. After all, the test dataset should simulate a real-world situation. Let's create a function that calculates the number of approved applicants for a given probability threshold. We define the function number of approved with one parameter, p, which will be the probability threshold. This function will return the number of borrowers for which the predicted probability of default is greater than or equal to the parameter p. With the help of this function, the number of approved applicants for every threshold would be returned by applying the n-approved function to that threshold. Then, the number of applicants that would be rejected equals the total number of applicants minus the number of approved. Once we've calculated them, we can find the approval and rejection rates. The approval rate for every threshold equals the number of approved applicants divided by the total number of applicants, and the rejection rate equals 1 minus the approval rate. Let's assume the highest level of probability of default we'd accept is 10%. In other words, the lowest possible probability of being good is 90%. With this cutoff, we will end up with 53.68% approval rate and about 46.32% rejection rate. How about a probability of default of 5%? Well, in that case, we'd end up with a 20.94% approval rate and a 79.06% rejection rate. Great! And that's how we set cutoffs using the estimated probability of being good. As we mentioned, we could set cutoffs using credit score instead. Since credit scores are discrete values, it is very hard to achieve the same level of accuracy. For instance, if we set the cutoff score at 585, we would approve everyone with a probability of being good greater than or equal to 89.969% actually. That would result in an approval rate of about 53.86% and a rejection rate of about 46.14%. Alternatively, if we set the cutoff score at 586, this would correspond to a minimum acceptable probability of being good of 90.0845%. In turn, that would result in an approval rate of about 53.23% and a rejection rate of 46.77%. All right. Let's just export the input string with reference categories data frame and the scorecard data frame to CSV files, and we're done. All right. For homework, you can play around with the cutoffs. Thanks for watching, and see you in the homework section.